Hello everyone and welcome back to another video on differential equations. So in the last video we covered the first one, that was real and distinct eigenvalues. Today we're going to be looking at the second category, and that is when we have complex conjugate eigenvalues. Since this is a 2x2 system, we're always going to have a complex conjugate, and so I guess they always kind of come in a pair here because we're solving a quadratic. So I really like to make these videos kind of straight to the point, so I won't really be doing a lot of derivations, a lot of theory. I'll give you kind of a general form and then we can just solve some problems. So I want to begin by just kind of walking you through what you want to do. So the first thing you want to do, as always, is set up your characteristic polynomial, or what I like to do, the MP method, which I have shown in a previous video. And so once you find that eigenvalue, you want to find a corresponding eigenvector. Now notice I've been very careful with my language here, where we only actually need one eigenvalue and one eigenvector. And with just a single, we can find all the information we need. So this process does tend to be a lot more tedious. So it's nice that we only need to work with a single eigenvalue and a single eigenvector. This formula over here might look a little confusing, and I will assure you it's not that bad when you actually do problems. So essentially, I can kind of walk you through what you can expect, right? So your eigenvector, right, is going to be some kind of complex eigenvector, right? I'm just going to be using all variables here, right? And hopefully at this point you're comfortable with like complex numbers, right, where you have some real part and some imaginary part. And so when you multiply that with something else, right, like let's just say on the right hand side we'll have something maybe that looks like e to the, let's say 2 plus 3it. I know I use some variables over there, right? But essentially, right, where you can think, so let me just underline. So this v1 over here corresponds here, and then this lambda 1t is kind of what we have over there, right? So we're going to use Euler's formula to break this up, right? And just a quick reminder, and that'll be Euler's formula says that e to the it is equal to I sine of t plus cosine of t. And this is really one of the most interesting things that comes out of, I guess you could look at Taylor's series to discover this, but again, getting kind of off topic there. So essentially what I'm saying over here is that we're going to have some real part, right? That's going to be something like this is going to be multiplied, and we're going to have some imaginary part. So what we want to do is we're going to split those into two parts. This little thing, RE, it takes some input and it spits out just the real part of it, right? And we say that one part of our solution is just going to be the real part of this whole thing multiplied by C1, and the second part is going to be IM, which is just the imaginary part multiplied by C2. If that looks kind of abstract and maybe confusing, that's completely okay. It's not a simple topic, but I think looking at examples will make this whole thing a lot more clear. So I'm going to actually do two things. I'm going to move this over here, and these two things are going to be very useful. So I'm going to bring those with us to the next page. All right, and let's look at an example, because those always help. Okay, that's quite big. Let me just shrink that down a little bit. Awesome. Okay, let's get right into it. So like always, first thing I'm going to do is find our eigenvalues. So that m is equal to 4, and then p is going to be 15 minus negative 2, which is just going to be 17. So then we have that lambda is equal to, we have 4 plus or minus square root of, I'm just going to write out all the work here, 16 minus 17, right? So we have m squared, right? So this is m squared minus p, right? And that whole thing simplifies. Everything in here is just going to simplify to I, because we're taking the square root of negative 1. So we have that lambda is equal to 4 plus minus I. By the way, if this just looks like some kind of wizardry I've just done, that's okay. Like I said before, that's something I covered in a previous video, so I'm not going to be going over that right now. Awesome, so we have our eigenvalue. Like I said before, we only need to use one, so just because I like the first one, I'm going to choose lambda equals 4 plus I, right? Why not? It has a plus sign in there, okay? And now to find our eigenvector, we're going to do what we always do, and we're going to subtract our eigenvalue off the diagonals. all right? So we're going to do 3 minus this whole thing. And that's going to end up, we're going to end up with negative 1 minus I. We're going to have a 2 down here. This is still negative 1. We're going to subtract that. We have 1 minus I. Okay. Now this might look a little unpleasant to you, and if you're seeing this for the first time, it's a little tricky. But one trick I think almost always works best is to multiply by the complex conjugate. I'll actually just go back here just for 1 second and just remind you maybe what a complex conjugate is, right? If we have something in the following form, let's say a plus bi, the complex conjugate, so we'll call this z. The complex conjugate is sometimes referred to as z bar, and that's going to be equal to a minus bi. All this we're doing is whatever sign is here, we just flip that. So if this is a negative, we flip it to a positive on the right-hand side. And the cool property is when you multiply this one with this one, your answer ends up being something that's completely real. There's a really nice geometric interpretation, but that would take too long to show right now. So what we're going to do is we're going to multiply this top row by the complex conjugate, and that's going to make things a lot easier for us. So here that's going to be negative 1 plus I. Right? We have to be very careful, make sure that this thing is the exact same and this thing is the exact same, right? We're not changing the negative one, but this sign over here, the inside, that needs to be changed. So I'm going to say negative 1 plus I times R1, and then R2 I'm just going to slide over. Now I know this looks kind of weird, but remember, negative 1 plus I is just some constant. So we're just doing elementary row operations, nothing new here. Okay, awesome. So we have that, so then we have 1. So when we multiply these first two, we have 1 minus I squared, which is just going to be the same thing as saying 2. Bottom one is still 2. That's looking good. And then the top, we have negative 1 times negative 1 is 1 minus I. Perfect. So everything has worked out very nicely, as should be expected at this point. We're going to move this over, and we're going to say R1 minus R2. And that wasn't too bad, actually. These can get a little tricky, but if you know how to find your complex conjugate, these problems are not bad at all. So finally, we have our eigenvector, and I'm going to say this is going to be 1 minus I, and then our bottom is going to be negative 2. And essentially the way I solve that is if we set this up as an equation, we have 2x, that's a bad x, so we have 2x plus, we're going to say 1 minus I y is equal to 0, right? And then if we plug in 1 minus I over here, and then negative 2 over here, it solves this, and we can have any constant multiple. Very nice. So we're in a really good spot right now, and let's kind of write out this whole thing now. So to recap now, our solution is going to look something like this. We have, we're going to say we have 1 minus I times, negative 2 times, we have e to the 4 plus it, right? So we have e to the 4 plus I t, right? And I know this thing kind of got stolen. I'm going to bring this thing back up here. I'm going to move this down somewhere where it's viewable. And I might have lost an h along the way. I'm going to put that back. Sorry for all the moving back up and down. All right. Okay. So this is kind of in a good spot right now. We're moving towards this general solution, right? And essentially what we've come to at this point is this part down here, the v1 e to the lambda 1t, right? And we're on our steps to the general solution. So this is our v1, and then this is our lambda 1t. Now, as is usually explained here, right, we want a nice solution that doesn't have any imaginary parts. So we're going to work now to get rid of that stuff, right? And what we need now is actually Euler's identity, this thing down here. So we're gonna rewrite this. I'm just gonna copy this left-hand part so I don't have to write that again. And I'm gonna say that this is equal to right, I'm gonna zoom in a little bit there. I'm gonna say that this is equal to obviously the same vector, nothing is changing with the vector, but I'm gonna expand this over here. So we have a real part, which I'm going to call e to the 4t, and I'm going to multiply it with e to the it, right? Hopefully this is nothing too crazy. This is just breaking up our exponential term. And finally, right, I'm going to notice I'm going to notice this thing down here, right? Now I want you to be careful because we're not going to always end up with something this nice where it's just like e to the it, but let's say, for example, instead we had something that looked like e to the 2it or e to the I2t. That would just be this same exact thing down over here, except this thing will become 2t, this thing will become 2t. So that's all there is. You'll see that in the next example, okay? So finally, I'm just going to rewrite this thing over here as I'm going to say I sine of t plus cosine of t. And I'm really running out of space pretty fast here. Plus cosine of t. Awesome. So we've rewritten this thing as something that's a lot nicer. It's going to be really a lot helpful for us. Okay, so we're really kind of in the final stages now. Thankfully, this has been moving pretty fast. I'm going to do something. I'm going to pull out this e to the 4t for now because it's only just going to create some more work and confusion. So now what I'm going to do is split this whole thing into a real part and an imaginary part, okay? So I'm going to put some parentheses over here, and I'm going to put a C1, and let's start with our real part, right? So this is kind of where you have to do some foiling. So we're going to have a 1 over here, and then a cosine t. So that's going to work out nicely. So I'm going to take cosine of t just like that. And then I also noticed that we have a negative I here and then another I. So negative I times I is going to be negative I squared, which is just 1. So we also have a sine t, which is good. So that has worked out nicely. And let's see what's next. So now we're going to be looking for our imaginary part. And sorry, before we move on to that, actually, let's also multiply on the bottom. So to get a real part on the bottom, we can only multiply -2 with cosine of t, right? So we're going to have a -2 cosine of t over here. And now we're going to try for our imaginary part on the right side, okay? So we're going to take this negative I and then cosine t. So then we have, we have negative cosine t over there. Negative cosine of t. And then what else do we need? Just going to move some things, make space. So negative cosine t, we need another imaginary part, and we're going to take this I sine t and then this 1. And that's going to become, we have just positive I sine of t. Sorry, I'm just making sure because there's a lot of places where you could potentially go wrong here. Okay, that looks correct. So we have positive sine of t. And then finally multiplying on the bottom, we have -2 sine of t. Awesome. Very good. All right. And that's essentially all there is to it. Now, obviously, if you were to maybe do this on exam, you can pull this e to the 4t and multiply it in. But at this point where we are right now, this is a completely complete. This is a valid solution. And this is something that would be totally okay. So let me actually just box this in like I had before. I think that might be helpful. But yeah, that's essentially what you got to do on these kinds of problems. That's what it is. I've just noticed that pulling out the e to the 4t, the real one, just makes it a little bit easier so you don't have to write it again and again. And that's essentially all there is to it. All right, so moving on to our second example. I know in the last one I kind of was given some more details and stuff, and this one maybe I'll just kind of get to the point. As always with these videos, please try and do these on your own before I work through them. Like I tell students all the time, I think you can really succeed and do best when you've kind of struggled through some problems. That gives you more insight into maybe what kinds of things can go wrong, what kinds of things are particularly tricky. But all that being said, let's jump right in. Let's see. So we have our m here is just going to be 1, right? 3 minus 1 is 2. Average of that is just 1. And then our p here should be, so we have -3 plus 13. So our p is going to be 10. So we have that lambda is equal to 1 plus or minus square root of 1 squared minus 10, which is just going to be negative 9. And so our eigenvalues are going to be 1 plus or minus 3i. Very good. Okay, now let's go ahead and try and find some eigenvectors. So I'm going to do like last time. I'm going to say, let's search for lambda is equal to 1 plus 3i, because pluses are nice. Why not? And oops, I'm just going to subtract that off the diagonals. So we have negative 1 minus that, which leads us to negative 2 minus 3i. We have a 13 over here. And then this one's going to stay negative 1, and subtracting from that one, we have 2 minus 3i. Please be very careful when you're subtracting these things. If possible, maybe do it on paper. Don't do it all in your head, because you can get a little confused with the different things going on over there. Anyways, multiply by the complex conjugate on our first row. So we're going to say negative 2 plus 3i times r1. And the second one's just going to move over. So multiplying that out, we have 4 minus 9i squared, which is the same thing as 4 plus 9, which is just 13. And that looks pretty good to me. And so this is also, oh, sorry, that's not going to be 13. I'm going to write it in kind of a nice way for us. So I'm going to write it as the following. So we have, let me show you what I'm going to do. So 13 is here, but we're multiplying that whole thing by this. So if you pull out a negative 1 from here, it's just this exact same thing. So I'm going to write it as the following. This is going to be negative 13 times 2 minus 3i. And hopefully that makes it a lot more obvious that the top one is negative 13 times the bottom one, right? So I kind of wrote it in a special way so it looks more obviously like a constant multiple of the bottom. Very nice. So finally, I'm going to call this top row R2, and I'm going to say R1 plus 13 R2. So that worked out quite nicely as expected. A really good check with eigenvectors, if you're not able to like reduce everything to a row of zeros in the bottom, that means you found your eigenvalue incorrectly or you plugged it in wrong. So that's kind of a nice way of checking that. Very good. And so what can we say from here, right? We can rewrite this. We can say that 2 minus 3i times y is just equal to x, right? And the way I got that is we have a negative sign over here, so we can just slide it over to the right. So rewriting that as a vector, if 2 minus 3y, so we can just say that this should satisfy our equation. And you can actually just do some matrix vector multiplication. You can multiply this matrix by this vector in this order, and you'll see that that's equal to 0 for any constant, right, that we might put out over here. So that means we're in a good spot. Yeah, sorry, I just want to double check this because these things can go wrong. Okay, looks good to me. Awesome. So now we're really in our final stages over here, right? So I'm going to write out, we have 2 minus 3i times 1, and that's going to be multiplied by our eigenvalue, which is e to the 1 plus 3i. So I'm going to rewrite that quite a bit, right? I'm going to say e to the t, and then we have e to the 3it, right? So that then we can rewrite as I sine of 3t. This is an important point. Make sure you don't forget this. Whatever is kind of in the exponent is coming down inside the sine and cosine. So that's essentially what we have there, right? Like before, I'm going to do something where I leave the e to the t outside because it's just easier, less having to write things out. And so we're going to have e to the t, and I'm just going to put that parentheses there. And let's begin. Let's have C1, right? Let's start with our real part. So we have a 2 and a cosine of 3t, this and that. And just write that down. So we have 2 cosine of 3t. Next we have our negative 3i, and then our I over here, which is just going to become 3 sine of 3t. Oops. looking on the bottom, we're going to get a real part when we just multiply our cosine with 1. And that's just going to be cosine of 3t. Let's move on to the imaginary stuff. And that is going to be, we have negative 3i and this, so that's going to be negative 3 cosine of 3t. And then we're also going to have 2 and then I sine. So we're going to say plus 2 sine of 3t. And yeah, you can definitely see at this point that there's a lot of writing, and you need to be careful that you don't make any mistakes with this I multiplication. But otherwise, these problems aren't actually too much worse than the stuff you've seen before, hopefully. So if you're having trouble with these problems, definitely recommend looking at the real case first. The real and distinct eigenvalues case. So that's the video before this one. Cosine and 1, so that becomes down here. Sorry, let me make sure I did that right. I don't know why that doesn't look... Oh, yes. Okay, so I almost made a mistake there. So here we're looking at, we're looking for imaginary stuff on the right-hand side. So we should get I and 1. So that should be sine of 3t down here. That's good. Yeah, I was going to say what's down here and here generally doesn't match. So that's a good, I guess I checked myself there. Okay, and yeah, that's essentially it. That's our general solution. Let's box this whole thing in. That's pretty much all I had planned for this video. If you saw a mistake somewhere, maybe something didn't make too much sense, please feel free to leave it in the comments. My channel is really small right now, so I really appreciate any feedback I can get. But that's really what's going on in these kinds of problems. Hope that was helpful. Thanks again for checking it out. Recommend this to your friends maybe. And yeah, have a great one, guys. Thanks.